Well, good afternoon to you all again. Now it's time to begin our presentation. So, as an introduction, we are glad on behalf of the Young Professionals Special Interest Community to have you all here in this YP webinar series. So today we will start the session with the presentation Understanding Site Selection for CCS with Global Case Studies. Thank you all for participating in this first activity. Today, then, we are counting on the participation of Carrie Holloway. Carrie is on the EAGE Professionals Committee, and she has a first-class master's degree from the University of Oxford in Earth Sciences. She has worked in SLB for over 5 years and is a senior geologist in carbon solutions. Carrie works on CCS and new energy projects globally, mainly at the site selection and subsurface evaluation phases, and she specializes in screening and ranking studies as well as geomodeling. So thank you, Carrie, for joining us today, for giving us your time, and for sharing your knowledge with all of our attendees. Welcome, and the stage is yours.
Thank you so much, Maria, for the introduction and for organising the webinar. So I'm just going to start with a few slides introducing the EAGE Young Professional Special Interest Community, and then we'll move on to the technical webinar and have a Q&A before closing. So the EAGE YP community is the network of young professionals aged 35 or below who are interested in sharing and discussing advice on career development, work opportunities, and skills as well. So it was established in 2013 and currently has around 2,500 members. So the community is also open to all members, regardless of age, even though we define a young professional as below 30. We really encourage those who are more senior, who wish to support and engage with the YPs to join us. And if you want to hear more about our activities, join on the LinkedIn page. So I'd like to go for a quick introduction to the current committee members for the YP committee. So we have Bridge, who is the committee chair from the Polish Academy of Sciences. We have myself and Ruth from SLB. We have Jonathan from the University of Texas. We have Sayo and Shi Yong To from Heriot-Watt University. We have Satesh from Petronas, Yuri from Aker BP, Happiness from the University of Po, and Aditya from RGIPT. So hopefully you'll meet some of us at the annual, as well as interact with us through our updates on the LinkedIn page. So in terms of activities, we have the YP special session at the annual. We also have a mentoring program in collaboration with the EAGE Women in Geosciences. We also do educational and networking events and collaborations, such as the webinar series, and we try to provide news, careers advice, and job vacancies. So a quick note on our mentoring program that I've been proud to help organise this year. So this is a one-year career development exchange process for pairs of EAGE members, matched based on their goals and preferences. So participants have access to career and personal development, career transition, work-life balance, as well as learning technical and soft skills. So I hope to encourage even more mentors and mentees to sign up this August for the 2025 programme. And we've had a great success in the 2024 programme with 46 mentor and mentee pairs matched from all around the globe. And it's great to see so many students and young professionals as mentees and so many mid-career and senior professionals as mentors. Additional upcoming activities next week in this webinar series, same time, we have Liesl, who is in geothermal exploration and development, who is giving a fantastic talk on this topic. We also have a special session, Attracting and Retaining Talent, at the EAGE Annual. So if you're attending in Oslo, please make sure you come to this because we'll have some fantastic speakers there. So now I'm going to move straight into the technical part of the webinar. So I'm going to be presenting on site selection for CCS. So as Maria said, I'm Carrie Holloway. I'm a senior geologist with SLB Carbon Solutions, so working on CCS projects globally. So the agenda for today, I'll talk about what is CCS, why do we need it, how we can select the best site for CCS via screening and ranking methods. I'll talk through some global case studies that we've worked on, and then I'll end with a Q&A. So please type any questions as they come to you into the chat, and then Maria will be able to pick them up for us at the end, or we can have an interactive session. So what is CCS? So CCS is the capture of CO2 from either emitters or directly from air in some cases, and then removing it from the atmosphere via injection into the deep subsurface. So once CO2 has been captured via mechanical and chemical processes, it's compressed and transported along pipelines or via ships to the injection location. Here it's injected at depths of around 1 kilometre or more underground into either depleted oil and gas reservoirs or saline aquifers. In some cases, also coal seams or basaltic rock. CO2 is currently being stored in both the onshore and the offshore environments. CO2 injection is also being used for enhanced oil and gas recovery, in which case it's encompassed in the acronym CCUS, where the U stands for the utilization. So other examples of utilization would be in chemical or food industry, in which case CO2 is not permanently sequestered. So this is why the distinction between the CCS and CCUS is important for evaluating the actual environmental impact of the captured carbon. So how does the CO2 stay in a saline aquifer or a reservoir once it's been injected? So there's 4 key trapping mechanisms. So when CO2 is injected, it will displace the brine and migrate in response to buoyancy forces and the pressure gradients. So as the reservoir brine imbibes back into the pore space, you get these small isolated blobs of CO2 which will be trapped by capillary forces. So this is known as residual or capillary trapping. And studies have shown that, especially in the early stages of injection, this can actually account for up to 95% of the CO2 in the reservoir. And it's the most important process for CO2 immobilization and CO2 storage security. So the majority of operating and developing projects are relying on this trapping mechanism. We also have our traditional structural and stratigraphic trapping, which is where CO2 is trapped buoyantly by impermeable cap rock and also a closed structure, for example, an anticline, a fault-bounded block, or perhaps a pinch out. So this is more like the traditional oil and gas traps. Solubility trapping is when the CO2 actually dissolves into the brine. It becomes in the aqueous phase and actually becomes denser in water and sinks out. And this is a slightly longer term process. When you inject CO2 in a supercritical phase, it will eventually, or some of it, will eventually dissolve into the water and be more secure. Mineral trapping, this is when you actually get precipitated minerals due to the interaction with CO2 in the reservoir rock. This depends largely on the rock type and the injection scenario. For example, in Iceland, what they do is they dissolve the CO2 actually in water and then inject this brine into the basalts, and the basalt reacts with the CO2 in the brine and precipitates carbonates. So the CO2 is actually stored as rock. So if we consider the majority of the projects being developed for CCS, we can consider splitting them into 2 main categories. So we have our structural trapping and we have our non-structural trapping. So a structural trap is your typical 4-way closure, your anticline. Often these will be previously explored for petroleum resources. And the advantages of using a structural trap are that you have a more predictable plume geometry, you have a simplified MMV, you know where your spill points are and where you expect the CO2 to end up. And these are often well characterized, either by a dry well, a wildcat well, or and/or seismic as well. Alternatively, you can actually inject CO2 where you have just flat strata or slightly dipping strata with no structural control. The advantage of this is when you inject the CO2, you have an open boundary. So the pressure actually can dissipate, which reduces the containment risk and can also increase the capacity. You tend to avoid faults or fractures related to structure this way as well. You may also be away from any exploratory wells, so there could be a lesser issue for well remediation. So I would say the different approaches have been noticeable geographically from the context of both geology and regulation. So in the US, the focus is storage in large onshore basins in deep saline aquifers, which tend to be either flat or slightly dipping and actually avoiding the areas of structure. In Europe, the focus is more on depleted fields and structures that have previously been assessed for exploration or for natural gas storage. So that brings us on to the risks of CO2 containment, which is the risk of the CO2 actually moving out of the storage complex and into shallower formations, or even in worst case scenario, leaking to the surface. So how can we mitigate or reduce those risks? We want to inject at depths so that the CO2 is in supercritical phase. And this is around 800 meters or more, depending on your pressure and temperature gradients. We also want to inject in an area which isn't seismically active and in a region where injection is not likely to induce any seismic activity. We tend to want to avoid faults, especially faults which are open or are conduits to flow, or could be reactivated actually during injection. We also want to avoid many legacy wells, especially old wells or deviated wells that penetrate the storage complex and could be a risk for leakage. Anything that does penetrate the storage complex, we need to consider for remediation, for example, with CO2 resistant cement. We also want to avoid impacting any ongoing subsurface operations, such as petroleum production, gas storage, or mining. We want to avoid a cap rock which has fracture pathways or could be prone to induced fractures with the injection of CO2. We want to limit dip, usually to, we say, 2 degrees or less. A high dip will result in rapid migration of the plume due to buoyancy forces. A low dip can be advantageous in terms of monitoring. We may understand more where the CO2 is going to end up as it migrates slowly up dip. We want to also consider surface factors, so restricting CCS projects to areas of low population density and assessing the environmental impact on the surface. And most importantly, understanding the overlying aquifers that are potential sources of drinking water and ensuring that they are protected from any potential leakage, for example, by primary and secondary sealing formations. So why do we need carbon storage? So 36.8 gigatons of emissions were emitted in 2022, with only 40 million tons being captured. So this is less than 0.1% of the emissions. We believe that over 22 gigatons of this is addressable by CCUS, so 60% of the emissions should be addressable. CCS is vital to decarbonize and to meet our global targets for emissions to prevent accelerated global warming. And CCS is arguably the only technology capable of reducing large-scale emissions from many different industrial sources. CCS also has the unique ability to actually be retrofitted onto an existing plant to allow them to clean up their emissions without impacting their operations. So the Intergovernmental Panel on Climate Change and the International Energy Agency have both evidenced the critical role that CCS must play in meeting global emission reduction goals. So this slide comes from the Global Status of CCS report. So I recommend, if you haven't already, to check this report out. You can see that the number of CCS facilities in the development pipeline has increased significantly in 2023, with 11 new facilities commencing operations and 15 new projects in construction. So as of July 2023, there are 392 projects in pipeline, representing 102% year-on-year increase. These are from different industries, from power, heat, oil refining, gas processing, iron and steel, hydrogen, some direct air capture, some from chemicals, cement, or biomass. So they're from many different industries. We can see on the right the top 5 locations for number of CCS projects in the pipeline and how this is actually accelerated year on year. So now we're going to talk about how we actually find our best site to store CO2. The first thing we need to do is screen a region to highlight suitable sites for storage. Then the next step is we rank these sites using a comprehensive list of criteria to assess which site or sites have the best potential and we can take forward. So screening and ranking is the first step in any carbon storage project. It's how we find the most suitable site to optimize the success of the project at an early stage. So once a site's selected, we can then evaluate it in more detail and move forward into our final investment decision. As we move forward, we're going to design and build the project and then eventually move to operation. The MMV, which is the measurement, monitoring and verification, this is going to be integrated throughout all phases of the project lifecycle alongside the data management and modeling. So what are the objectives for our site screening and ranking? So to assess if CCS is possible, to provide a regional or country level assessment, to minimize subjectivity or uncertainty if we were just looking at a single site, to optimize our design and investment, to estimate preliminary costs, and also to help prepare for licensing rounds. And it's very complex, so there's many factors that must be considered to get site selection right. So having access to the data we need, analysing all the performance criteria, looking at geological uncertainty and variations around the world. So we have to use specific tools and workflows to validate all our data with an emphasis on risk identification and using sensitivity and uncertainty analysis. So what are we actually looking at when we're screening and ranking? So we're looking at both technical and non-technical factors. Both are important for the viability of a project overall. So in terms of the technical factors, we're looking at capacity, injectivity, containment. So capacity is how much CO2 can we store? And this is based on the available pore space, the efficiency factor, and the CO2 density. In terms of injectivity, we're looking at how easy will it be to actually inject that CO2, how many kilotons per year can we actually inject per well. And this is going to be related to the connected pore space, the pressure conditions, the permeability of our reservoir, and also relies on us optimizing our injection strategy, so the placement of wells and the number of wells. Then containment, so this is the ability to store the CO2 safely and permanently. And for this, we want to consider geomechanical factors, so the critical pressure that we can put on the seal, or on any faults or potential fractures that could cause leakage. We also need to consider in containment factors like legacy wells and suggest any plans for legacy well remediation. Other criteria that's also critical to a project is understanding our monitoring program, understanding how we need to transport our CO2 from point to point, how much it's going to cost, looking at the legal aspects, so what we need to get a permit, whether we need to apply for pore space or a license block, understanding public opinion, especially if we're onshore, looking at population density and the history of subsurface operations in the area. And it all comes down to economics in the end. So what are the funding regimes in the area that we're looking to do our project in? So this is the general workflow for how we go from our data all the way through to actually deciding whether we evaluate a site or not. So we start with data, and if we only have sparse data, we might not have enough to do any kind of geological modeling. We might then select our site and go straight to ranking. If we have enough data, this could be from public data, this could be data we're purchasing, for example, well and seismic data, it could be the data we hold internally. We can feed this into either our 2D structural modeling or our 3D basin modeling. And this I'll demonstrate with some of our case studies. We produce these chance of success maps. Now these highlight the areas most suitable for storage, of which we could select multiple sites and run through our ranking process, in which case deciding whether we want to evaluate the site further or not. So how do we screen? So we screen by a process, or one process we use is play chance mapping. And this was a workflow that's been adapted from oil and gas exploration that we now apply to CCS. So it's integrating a lot of different data and data sources to create a probability map, characterizing the area based on a number of criteria. So this map will identify areas where we have a high potential for storage of CO2. And you can see in the flowchart, we can actually create both subsurface maps and surface maps. Subsurface maps consider our storage zones, our seals, our reservoirs or aquifers, our data availability, our subsurface risks as well. And surface factors could include things like where we have protected lands, where we have water bodies, topography, or population density. And it's not just restricted to these points. It will be different for each project we do based on the data, based on whether it's onshore and offshore, based on the legislation, etc. So here's a public case study that was performed in the state of Sao Paulo, Brazil. So here we're within the Paraná Basin. So multiple storage reservoir and seals have been mapped alongside the data availability, the geological risk, and the surface factors. So we've combined them into what we call a COS map, or a chance of success map. And we can see areas in red which have low or no chance of success. These are areas where we have protected land, rivers, population, and this large area here is because we are outside of the critical depth for which we could store CO2. So the basin is not deep enough in these regions. In the areas highlighted in green, this is where we have good storage and sealing formations. We have low subsurface risk. We have good data availability, and also the absence of water bodies, environmentally protected areas, or densely populated regions. So from here, we can actually pick sites that we could store our CO2 in. The second example comes from Egypt. So this is a project that was run as a collaboration between EGAS, Shell, SLB, EUG, and the University of Aberdeen to accelerate the screening offshore Egypt in support of COP27. So it was a wide-ranging project which considered the multiple elements of storage, so looking at emission source, social impact, infrastructure as well. And at the core, it was a play-based approach, as I discussed in the previous example. And this resulted in identifying over 622 million tons of prospective CO2 storage. So the results from the G&G analysis, again, I integrated using a play-based approach. So mapped reservoir, seal, and injection parameters are used as proxies to define success. In this case, we have formation depth as a proxy for the supercritical condition. We have a seismic cube, so the RMS amplitude map, as proxy for reservoir and seal rock presence. We also have reservoir thickness and porosity, amongst others, are used for a proxy for quality. So they're converted into a chance of success map and stacked to derive the final map for each play. And then potential sweet spots are highlighted and their capacity estimated. And we did a similar process offshore in the southern North Sea for the chance of success maps, where we integrated net to gross, reservoir thickness, depth, presence, seal thickness, and fault maps as well, both for the Bunter and the Rotliegend. And you can see how, again, we're highlighting those areas of greatest potential. Now we can also do screening using our 3D basin modeling. So this is more investigating the occurrence of structural traps. So this is quickly identifying the CO2 migration and leakage pathways using rock properties and the invasion percolation method. And we can create a 3D basin model and run quick simulations. We can also quantify the trapping mechanism at a regional scale and calculate the CO2 geological storage suitability maps, or the chance of success maps. So this example is from offshore Norway. This is the Utsira Formation, where we have the Sleipner project. So this is the top of the Utsira reservoir, and you just saw the structures that are closed being picked out. We have seismic data here. So we have the rock properties, and we can actually see the CO2 migration pathways by injecting into each of these structures that was identified, and we can calculate capacity for each of these structures. So you can see we built this 3D model using the structural maps for each horizon, and also we have a facies model based on the shale percentage in the Utsira. So from our model, we can output geological properties like temperature, porosity, permeability, capillary entry pressure. And we can also run this type of CO2 rapid simulation. It's just based on Darcy flow. But we can actually see from point source injection where the CO2 would actually end up, so that we can understand the migration pathways, any leakage risks. So we do all this actually using our Petramod simulation, but we can do the basin modeling and then export the results into Petrel, which is a software many of us are more familiar with. We can then integrate the results of this into our play chance mapping, similar to the previous project shown, and pick out those sites that have the best potential for storage in a basin. So once we've actually picked a few sites, picked some actual locations where we could store CO2, how do we rank these in terms of choosing which is the best? So we have a few challenges when we're ranking. So we want to ensure that we're including all the relevant criteria. We've actually generated or developed a cloud-based tool that has a comprehensive list of every criteria that we may want to consider when we're looking at CCS projects. And some of these criteria are quantitative and some are qualitative, but they can all be compared by using this multi-wise comparison using the AHP and TOPSIS mathematical algorithms. So we can also, all the criteria are arranged in a hierarchy. So we have a category and then subcategories underneath. And we can assign a weighting to every single criteria as well, because some are more important for certain projects than for others. And we also have this process standardized and in the cloud, so it accelerates our decision making. So the ranking is this process here, and it actually comes after the initial scoping, after the screening, and once we've done our multi-domain analysis. All of our domain analysis feeds in to our ranking so that we can decide which site to evaluate. And this is not restricted just to subsurface. We're also looking at surface, we're looking at transport, we're looking at economics and many other factors as well. So this is the cloud tool, the carbon storage ranking tool. We have a list of over 140 criteria from which we can select which criteria we want to use in a project. These are arranged in a hierarchy. For example, it's split into technical and non-technical. Underneath technical, we'll have capacity, injectivity, containment. Then underneath capacity, we would have things like the openness of the reservoir, we'd have the pore volume, we'd have the thickness, etc., the efficiency factor. So it's arranged in this hierarchy, and we perform weighting in the weighting matrix table. So then we can actually add our site. So instead of a map-based scenario, we're looking at individual sites. So we set the longitude and latitude of each site, and then we can enter in the site parameters. So the areal extent, the reservoir gross thickness, the porosity, as either a single value or as a range of values, or we can pull it in from our Petromod software. In terms of site ranking, it will take all these criteria that we enter, combine them using AHP and TOPSIS, and give us a final score for each site. And we can also look at the different factors that impact the score for each site. We perform sensitivity analysis, so looking at how changing the weighting could affect the overall score, looking at also how taking different values from a distribution can affect the score, and also run uncertainty analysis, so understanding if we run, say, 1,000 Monte Carlo iterations, taking different values for all the properties where we have a distribution, we can then see the overall score distribution and output a P10, P50 and P90 score. So an example of this ranking analysis was a project we did for a client offshore Trinidad and Tobago. So the project aimed to evaluate and rank 3 offshore assets in Trinidad because there's actually a bid round going on at the moment. So the comparison was made between the 3 sites, which we'll call A, B, and C. And it was made between these sites and also the Illinois Basin and the Utsira Formation, where we have currently operating project. So these were our benchmarks. So the solution allowed for the relative comparison to those existing sites. We can see actually that site C scored the highest out of the 3 Trinidad sites and was comparable to Utsira, so where we have Sleipner. Especially, you can see it's comparable once we look at our score distribution plot. We can see clearly as well that the site in Illinois scores much higher, and the other sites, A and B, score lower. So by doing this type of ranking, we can confirm that site C would be geologically and well, technically and non-technically the best site to pursue in the region for CCS. So this is actually my last slide, so we'll have plenty of time for Q&A. So I've talked a lot about screening and ranking. Due to CCS being a rapidly growing industry, this is actually where a lot of the projects are sitting right now, in the initial phases, pre-FID. So some projects, for example, the UK cluster projects and some of the projects in the US that they've almost got their permits now, they're more in the site characterization, well, in the site evaluation and design phase, which includes the evaluation, which includes the characterization and the performance assessment. So in this phase, this is where they will be acquiring additional data, so drilling stratigraphic wells, shooting new 3D seismic, building up a 3D geological model, providing coupled flow and geomechanical simulation. They'll be also performing well design and deciding on an injection plan, etc. So once this is complete and FID has been taken, then the builds phase starts. The next steps will then be moving towards operation. So first we'll do a baseline monitoring, and then during operations a continued monitoring. And usually planned injection is around 30 or so years. Projects that are currently injecting are in that stage are projects like Sleipner, Schnøvit, Aquastor, Gorgon, ADM, Quest, etc. So there are projects in the operational phase. So after operations, we'll then move into a post-operational monitoring phase to ensure containment over the next 50 or 100 years. So that depends on the regulations. And eventually into site closure. So that is the path to a successful CCS project. I hope you found that useful, interesting. I've given you a bit more of an understanding on the site selection for CCS. So please, I open the floor to any questions you might have, whether it's generally about CCS or about what I've presented today. So yes, thank you very much for your time, and feel free to unmute yourself or post anything in the chat.
Thank you, Carrie, for your presentation, for dedicating this time to talk more about CCS. Of course, all of our attendees are kindly invited to send your questions through the chat, or you can open your microphone, it will be okay, and we can establish a direct contact with the presenter. So please feel free to bring forward all your questions and inquiries.
We
Okay,
have
I
one
see
question. Yeah,
yes.
from Martin Pereira. So, Carrie, it says, can you please make some comments on which of the 4 trapping mechanisms is the more successful or the best? Do you have a ranking for that?
Sure. Thank you so much for your question, Martin. So in terms of the trapping mechanisms, it depends on your geology, and it depends on your project, so your geological environment. In terms of the most important trapping mechanism in general is the residual or capillary trapping. So as I said, studies shown that this can account actually for 95% of the CO2 initially in the reservoir, and this is for a normal case, a saline aquifer case where you have a cap rock but not necessarily a structure that's trapping. And then you'll get a plume geometry, something like this. This is a nice image from the University of Oslo. If you're injecting completely flat strata, you will get a CO2 plume that is generally buoyant and stops at the seal, and the lateral spread is contained because of this residual capillary trapping. Now, if you have a slight dip, and this is exaggerated, this should be 2 degrees or less, otherwise your plume might really shoot upwards. Again, the CO2 is contained by this residual or capillary trapping. Now, if you do have some sort of structure that you're injecting into, this can help determine exactly where the CO2 is going to go, because you can inject the CO2 up to the spill point, in which case the CO2 may sit at the top of the structure in terms of a free phase. You'll probably inject down dip in the structure due to the pressure buildup. You don't want to inject at the crest, so you'll inject down dip and then the structure will fill up. So in this case, the structural trapping is very important. Now, solubility trapping, this happens in many cases, but is a much smaller percentage of the CO2, and it's the CO2 actually dissolving in the water, but this will happen over decades or longer. It's thought that this won't be a hugely important phase of trapping, especially early injection. Now, mineral trapping is a really interesting one. This is when CO2 actually turns to rock. So you could say this is the safest way of storing our CO2, because the CO2 is actually becoming a carbonate mineral. So it's not going to be leaking anywhere. Now, this only happens in, it only happens at scale in unique scenarios, for example, in Iceland, and it happens more there because they actually dissolve the CO2 in the water to start with. Instead of injecting as a supercritical phase, they dissolve the CO2 in water, which makes it more reactive with the basalt, and then it reacts with certain minerals in the basalt and turns into some sort of carbonate mineral. So all these trapping mechanisms are important and will happen to some extent in all projects, but it might be that we have 95% residual trapping and a couple of percent solubility trapping in certain projects. But other projects, like in Iceland, I don't know what percentage they are mineral trapping, but it's probably over 50%. So it depends on your project. Yeah, hopefully I answered your question.
Thank you, Carrie. We have another question in
Okay.
the chat from Maria Lorenzo. Thank you so much, Carrie. Excellent presentation. About the Brazilian study case in São Paulo, could you point out some critical points in the CCS evaluation?
Some critical, what, sorry?
Some critical points in the CCS evaluation, she said here.
Critical points.
Yes,
Yeah.
Points?
Okay.
Points? Okay, sorry.
Sure. Okay, so here we were looking at the onshore basin. So the critical points was actually where we had formations at depth to store the CO2. So the basin extends to around, well, just outside this red line here, because outside of this, we don't have a thick enough section of the basin to actually get that CO2 to the supercritical depths, which is at around 800 meters. So finding where we can store deep enough was very important. I'd say onshore as well, we have to consider all of the surface factors. So we can see some red, big red areas. These are where we have actually protected lands. Then this is where we have the rivers. So for an onshore project like Brazil, we have to consider where do we actually, where do we have to avoid because of surface features. Another unique thing about the Brazil project was we actually were quite constrained on what data we had. Unlike the other projects highlighted, we weren't looking at seismic. Well, we had the odd 2D line, but we didn't have a 3D seismic cube. So we were mainly looking at well data, and the well data is pretty sparse. So actually, one factor that was positive in terms of chance of success was the data availability. So having data there enables us to then de-risk a project compared to an area which is potentially suitable, but has no data because the uncertainty there is so high. So actually where we had existing stratigraphic wells or exploration wells in seismic, we ranked those areas as quite high. And this is different from an area like if we were looking onshore Texas, where we have so many wells, we actually try and stay away from the wells because these legacy wells become then a leakage risk. That wasn't really the case in Brazil because we have so little information. We want to be pretty close to at least one well where we have some information. So it's it depends geographically, which is most important factors to consider. Yeah. Thanks.
Thank you, Carrie. We have another question here. Let me check. Victor, in terms of injection and monitoring plan, what are the injection strategies for the CO2 storage? How will the injection rates, pressures, and volumes be controlled to ensure safe and effective storage?
Okay, so I didn't talk much about the monitoring plan. This is well, it's considered at all stages along a project. This is the MMV. So in terms of the strategies, it depends on project, but we need to have wells, monitoring wells, and these are wells that are monitoring both the injection formation and also higher formations as well, so that we can actually take pressure measurements and measure the presence of CO2 at a distance from where we're injecting. So we're making sure that our measurements are actually matching the model or the way we expect the CO2 to behave in the reservoir. So we can do that by wells and taking samples, and we also need to be sampling our shallow water as well. So maybe surface water or at least water aquifers above the containing formation. In terms of other methods, we're going to be thinking about 4D seismic. There's a really nice example in Sleipner where you shoot your seismic 3D survey every few years, and you can compare from one to the other and almost see the CO2 actually on your seismic. So understand in that way where the CO2 is within the subsurface and understand if it is leaking. So how do we ensure the injection rates and pressures and volumes are controlled to stay safe? So this is obviously key, and there have been projects where we have seen examples where we've actually started having some problems. For example, in Illinois, in ADM, when they first injected, they injected too deep. They injected right on top of basement, and that actually induced some seismicity. Now, seismicity is like mini earthquakes, so you can actually monitor for the seismicity to understand if you're inducing anything as you're injecting. In that case, the project was stopped because they monitored this seismicity, and then they injected subsequently in a slightly shallower portion of the formation where we weren't inducing any seismicity. In terms of the injection pressures, so we do full geomechanical studies to understand the critical pressure at which we can raise the reservoir to, in terms of at what point we may fracture our seal. This is especially important if we're looking at carbonates. These are more easily fractured. So we need to run not only simulations, but also laboratory tests to understand at what pressure we can actually raise our reservoir to, and make sure that our injection scenario fits that. So we always want to be in a safe zone, so at least 90 or 80% below the fracture pressure on any of our faults or seals. So I hope that answered. Yeah.
Thank you, Carrie. There's another question from Mattia De Luca. Hi, Carrie. Thank you for the presentation. Have you any comments on the effect of existing flow in the aquifer and how they impact the CO2 containment?
Okay, I guess you mean more hydrological flow in like the saline aquifers. So this isn't something that I have studied extensively. In general, the CO2, the main thing that drives the CO2 is the buoyancy and the pressure effects. So in general, the CO2 will move upwards and away from areas of higher pressure. In terms of the existing flow, that's something I'll look up, but I haven't actually studied that. So thank you for your interesting point. I'll look into it.
Thank you, Carrie. Another question from Joy Perez. Do you have some comments about the differences between the 3D static modeling characteristics in the oil industry and for CO2 storage?
Sure. So in general, we use a lot of the same technologies and softwares for our modeling from the CO2 and the oil and gas. The differences are with the CO2, we tend to be building these models up. So up to the USDW, the lowest underground source of drinking waters, and maybe even down to basement. So we need to actually, especially if we're in a saline aquifer, we need to confirm that we have a seal, whereas in oil and gas, if you find some gas, you know you've got a seal. So the difference is we actually need to model not just our reservoir, but we need to model everything above and below. And then we need to do our forward simulation to understand where that CO2 is going to go over time. So I think the main difference is we do very similar in terms of reservoir modeling, but we also really have to characterize the seal to understand if it will contain the CO2 and subsequently the formations above and the formations below, and understanding how they'll be affected. Thank you.
Thank you, Carrie. And the last question, Sasinon. Very good presentation. Can we do the site selection by using only geological surface data?
Okay, so we usually split the data into what we consider surface and subsurface. So surface, let me jump to that slide. Surface is anything where we're considering actually what's on the ground. So our water bodies, our topography, protected land and population. Maybe we know the surface geology, but if we don't understand the subsurface, then no, we can't do site selection because both of these are equally important. In fact, some may argue that the subsurface is even more important. So if we don't have any data to help us characterize the subsurface, whether this be well data or seismic data, then we're going to really struggle to actually choose a site. So what we can do is narrow down. We can make a surface map and say these are the locations that could be possible looking on surface data, but then the uncertainty in the subsurface would be very high if we didn't have any data there. So basically you'd have to drill a wildcat well, drill a strat well and see what you had. But it depends where you are. I mean, in a lot of locations, we do have data and deep subsurface data, mainly thanks to the oil and gas industry. But obviously areas where we don't, we may be able to get some sort of magnetic or gravimetric survey to just try and understand the depth to basement, because that could be a very minimum criteria, just finding out that we had the sedimentary depth to store the CO2. But really, if we don't have any subsurface data, we're going to struggle. So thank you for your question.
Thank you so much, Carrie.
Okay.
It seems that we don't have more questions from the audience or to you. So I don't know if perhaps anyone else wants to ask another thing. Okay, no, it seems that not, so I think that we can close the session. Obviously, if you want to say something.
Well, then, thank you, Jose, for also supporting our webinar. Thank you, Carrie, for being part of this exciting session. Thank you, all of you, for being part of this great activity. We hope to count on your participation in our next webinar coming on Thursday, May the 2nd, with Lisa Lewis. So thank you very much for joining us today and for engaging with the young professionals community. Thank you all for joining us and have a good day.
Thank you. Thank you so much. Thank you, Carrie. Hope to see you
Thanks,
soon.
Maria. Thanks.
Bye-bye. Thank you.
See you in 2 weeks' time for the
For sure.
geothermal. I look forward. All right.
For sure.
Bye for now. Bye bye.
Bye. Thank you all.